Alright, welcome back to the Neuro Symbolic Channel. I'm Shakarian, and today we'll be talking about a recent paper that came out of my group where we are abducing domain relationships from domain data. And this is applied to visual question answering. And this will be presented at ICLP, which will be held in Dallas, Texas this fall. And let's get right into it. Let's start with a little motivating example. So the generation of scene graphs is something that has become very popular in machine learning in the last few years, and there's been a lot of great advances. So the machine learning guys have gotten really good at going from an image to recognizing not just objects but their relationships. There's also been some great advances on this with vision language models as well. But one thing to keep in mind is, what if you have a specific domain that you need to answer questions about, and you have to have the objects classified according to that domain? So there's got to be like this prior knowledge. And what if you just don't have that readily available in the right format or whatever? Then you might not be able to answer questions in that domain. So if we look at this example, we see that there's this question: what is the color of the fruit to the right of the juice? So you have the image and you have the entities 55 and 57, which are representing the banana and the juice. And those entities have attributes associated with them. 55 is a banana, it's large. 57 is yellow, it is juice. But the issue is you can't answer the question because there's nothing in those white shapes that indicate that banana is actually a fruit. And so you need some domain knowledge. You also need domain knowledge about what is large, you need a domain knowledge about what is a color, because if you just know it's yellow but you don't know that yellow is a color, you also can't answer the question. And so we need this domain knowledge, which is shown in the shaded circles, in order to answer this question. And if it's not readily available, or your generalized knowledge doesn't have something for your specific domain, you might be a little bit out of luck. And so let's just throw some meat on this example. We have a little bit of notation. We have a scene graph, which we'll say is pi I, which is a collection of facts that the machine learning model has recognized. We also have pi q, which is the query that you want to answer. So we assume you have the scene graph, assume you have the query, and we have some other rules, pi r, which we'll call infrastructure rules. They're just things that help you answer the question. They're sort of mechanical, like things that like a Prolog programmer would write. And to complete this example, we have what the actual answer is that the result will be yellow. But again, that can't possibly be answered with the logic program I showed you in the previous slide. You need some additional logical facts, which are shown here in pi d, which just tells you what domains certain things belong to. And if you have those thrown in your logic program, now answering the question is just a simple deduction. But we don't have it, and we want to get pi d from data. So let's say we have this, and we can formulate what's called a domain abduction problem. So we have examples, which are pairs of the images in question, so the scene graphs for the image to be precise, and the queries in logic format. And then we have ground truth about what the right answer is. And then we have some common rules as well. And we need to find explanation pi d, which is the domain knowledge, which you saw in the last slide. And you want to find pi d, so when it's unioned with all the logic program for the scene, for the rules, and for the query for each I, then you get the ground truth entailed. Okay? But of course, for noisy data, you want to just do this for as many of the training samples as possible. That would seem reasonable. And the quantity here is actually accuracy, it turns out. So in the paper, we introduced just a very simple algorithm. It goes through the data in a single pass. It doesn't give an exact theoretically guaranteed accuracy, but it's efficient, and it gives you a, you could argue, a sound but incomplete result. Okay. And so how does this work in practice? Well, we did some experiments on this, and we compared baseline, the kind of accuracy you get on answers without learning that domain knowledge from the data, and we separated this into test and training data. So nothing in the test data was seen in what was used to learn PI-D, and we see what happens with using our domain abduction algorithm FastApp. When we have two versions, one where we have these additional fallback rules, which were just some additional infrastructure stuff that gave us like a 1% or 2% improvement in accuracy. But bottom line is, this is doing significantly better, like 10-20% better most of the time. And this is on these different query types. And so what happens if you don't have a lot of training data? Well, we see that we get to this high 70, low 80% accuracy with just about 10-20% of the training data that we used for this. We also see that the training time taken is directly related to the size of the domain, and this it trends about as you'd expect. As this you really can't count the first point. That's just kind of starting out at nothing. You're not gonna, with no training data. So when you look, disregard that, this is approximately a linear trend. Again, that's going to be very data dependent. You might have a query that causes you to abduce a whole bunch of stuff in your domain. That one query can take a lot longer than something that just requires you to abduce one thing. And so, but on the whole, these results are not unexpected, because this algorithm that we provide, it does a single pass of the data. So seeing something approximately linear, it seems about right. We also checked hyperparameter sensitivity, because you could kind of view this in a way as sort of like a rule learning thing, and it has a threshold on what we accept as being part of the domain knowledge. But even when we varied this, there was a threshold when we set to be, say, 50 percentile. It was more accurate than the others, but by about 1%. So this wasn't overly sensitive to that. So anyway, I hope you found that interesting. We think this has some really neat applications to Neuro Symbolic AI, particularly as you have a really nice vision model that produces a scene graph, but you need to complete the knowledge and you don't have the requisite domain knowledge handy. This is part of our metacognitive effort, Reasoning About Machine Learning, that's funded by ARO. We're really thankful to our sponsors. If you like this video, like and subscribe. Many more like it. Thank you very much for tuning in.